Hello, everyone. Welcome to starting our unit on evolution. I know you've had a couple of videos to kind of catch you up with natural selection and thinking about some of the processes that we describe when we talk about evolution. But today we're going to give an example of what does it mean to evolve and how do we have evidence of that, and what is a great example of doing that. Activity one is called the full course. For this activity, this is because it's the first activity. We'll kind of go back and talk about this as just a unit here. Have you ever wondered about the variety of organisms on Earth? How did they evolve? How are they related? Scientists investigate these questions by looking at patterns in data, gathering evidence for cause and effect relationships, using models, and constructing explanations for such phenomenon as the evolution of new species and the extinction of other species. In this unit, you will explore one such example that is so universal it has become a scientifically accepted theory: Charles Darwin's theory of evolution by natural selection. You will learn how populations of organisms change over time and how new species arise while other goes extinct. You will learn to interpret the many sources of evidence for the evolution of life on Earth now and in the past. You will also explore how evolution impacts us every day and how we can affect the patterns of evolution. So for this, I just want you to think about this answer or these questions. I apologize. Remember last year when we studied cells? So we did a unit on cells, and we talked a little bit about the kingdoms of life. And we talked about bacteria. And we did a little talk about viruses as well. And with viruses, you may remember that the unique part about viruses is they're not made of cells. So they do have a protein coat. They do have genetic information. Sometimes it can be the double-stranded DNA. Sometimes it could be the single-stranded RNA. But as far as viruses go, they are different than bacteria. And so when we think about antibiotics, what antibiotics are used for, against bio-life, antibiotics are used to kill life. And if viruses aren't technically classified as living, they're not going to work to kill viruses. And this really good example and piece of knowledge to take forward with you, especially in a time where we're living that a virus pandemic is causing lots and lots of changes in your life. So why can't we just take antibiotics to get rid of it? Because they don't work. Now, in addition to antibiotics not working, there is an additional side effect that's really negative for humans when we use antibiotics when we shouldn't, or when we take them incorrectly. So have you ever taken antibiotics? I'm sure most of you have. Strep throat can be bacterial. Ear infections can be bacterial. If you've ever had surgery, or sometimes when you get your teeth taken out, you take antibiotics. Anytime that you think you might get a bacterial infection or have a bacterial infection. And then do you remember last year that video on Alexander Fleming? So penicillin was the first fungi used as an antibiotic. And remember with Alexander Fleming, he had a bunch of petri dishes in his lab, and he left one uncovered and some mold flew in. And lo and behold, he noticed, hey, wait, where there's the mold, the bacteria isn't growing close to it. I wonder. And therefore the first antibiotics were developed. This activity is called the full course, and we are going to be talking about being sick with a bacterial infection and being prescribed medicine. Now, when you have a bacterial infection and you go to the doctor to get prescribed medicine, that doctor is going to check to make sure, in fact, it is a bacterial infection, which is why you get the throat swab like that. So they put that long toothpick, tongue depressor down your throat, or sometimes it's a toothpick type thing with the really long stick, and they'll take a swab of your throat tissue, and they're looking for possibly streptococcus. Streptococcus bacteria looks like those round little balls, those coccus balls. And strep throat is caused by streptococcus bacteria, and they're looking for that. If you have a red sore throat and you don't have any evidence of a bacterial infection, the doctor will not, should not prescribe an antibiotic. And this is why, with the thinking about the future of possibly online doctor appointments or virtual doctor appointments, there could be some disadvantages to that because I really want to know what I actually have instead of guessing. Like, oh, I usually get a sore throat and it always is strep throat, so it's probably strep throat this time. Well, maybe not. And if I usually get strep throats and as I always get strep throats, maybe I'm the antibiotics, maybe that's too much. And so it's kind of like now, right? Like the only way to know if you have COVID is to get a reputable, reliable test. And that is because that has been a big challenge for us because we aren't testing everyone. And so when people say, well, I have this and this and this, okay, you probably have COVID. All right, but I don't really know. The bacteria that causes sicknesses is completely different than the viruses that causes sicknesses. So viral infection, bacterial infection, there you go. Activity 1. Sasha has a serious respiratory infection. Her doctor has done tests that show the infection is caused by bacteria, and he has prescribed antibiotics to help fight the infection. Sasha, I think you will start to feel better in a few days, but it's important you keep taking all the medicine even after you feel better. You must finish it all. Don't stop and don't miss doses, warned Dr. Torres. Why? She asked. I don't keep taking other medicines after I feel better. There's a real crisis developing with antibiotics. Please take them. People take them when they don't need them or take them for a while and then stop. This causes bacteria to evolve antibiotic resistance. Doctors and researchers are very worried about this. What happens when the bacteria are resistant? Asked Sasha's mother. Dr. Torres replies, the antibiotics don't work against the resistant bacteria. Last year, our clinic had 4 patients with infections we used to be able to fight easily. 3 of those patients had to stay in the hospital and take antibiotics for a very long time before they got better. The other patients didn't make it. You know, I just saw a story about that on TV, said Sasha's mother. I'm beginning to understand that antibiotics are different than other medicines. I'll be sure to take all the pills. Excuse me, said Sasha. So, something about medicine, something about bacteria evolving. So, our guiding question, what happens when a person does not take antibiotics as prescribed? We are going to now set up an experiment, obviously virtually, where you're going to watch a video of this happening, and I'm going to explain what you're going to be looking for. So you're going to imagine that you're sick with a bacterial infection. Your doctor prescribes you antibiotics to be taken every day for 8 days. You've probably been on some that are for 10 days, maybe even 5 days. So there's a range of how long. You would have gotten colored discs, and you would have gotten green discs that represent the least resistant bacteria. So resistance is how strong I am in stopping the antibiotics from killing me. So if it's least resistant, I'm easily killed. Resistant, normally killed. Extremely resistant, real hard to kill. So there's green, blue, and orange. You're going to get a die, a number cube, and each time you toss the number cube, it's time to take the antibiotic, and then the number cube will tell you what to do. And I'll show you that setup in a minute. So real quick, and pause the video, and in your science notebook, please make this data table with the toss number. The toss number is just 1 through 8. You'll have 8 days. The least resistant bacteria, we're going to start out with 13 green discs. Resistant bacteria will start out with 6 blue, extremely resistant 1 orange. And so in your body, you have 1 extremely resistant bacteria, not really causing a problem. Your body can handle it. You have a total of 20 bacteria in your body. The antibiotic is obviously going to start killing the least resistant first. Our goal is to kill all of the bacteria that is causing this infection. Why are there different resistances of a specific bacteria? Well, we're going to watch a short video on that as well. And we're going to think about that idea that organisms have variation. Some bacteria have variation within their population that allows them to survive better. So when you watch those videos on variation, that variation leads to the different resistance levels. Okay, let's watch this.
Full course. Begin with 20 discs, 13 green, 6 blue, and 1 orange. These discs represent the harmful bacteria living in your body before you begin to take the antibiotic. It is time to take your antibiotic. Toss a number cube and follow the instructions in the number cube key. You took the antibiotic on time, so bacteria are being killed.
So if you'll notice at the very top here, if you roll a 1, 3, 5, and 6, that you did what you're supposed to do. The antibiotic was in your system and was able to keep up with killing the bacteria. And so you remove 5 discs. You start with green because those are the easiest to kill with their variation. And then you move to blue and then you move to orange. Well, then, of course, during the night, so I take my antibiotic and then I'm waiting till the next day to take my next dose. The bacteria are obviously multiplying. In this model, that multiplication is just with 1 disc. And so if I have a color disc in my body or in my model, then I'm adding another disc to show multiplication. And in this model, again, remember, we are trying to show a simple explanation for how bacteria works in your body. It's, remember the saying, all models are bad, some models are useful. And so you're thinking about what's useful about this model. What does it show that actually helps us understand?
Remove 5 discs. Remove all of the green discs first, then the blue, then the orange. The bacteria are reproducing all the time. If one or more bacteria of a particular type are still alive in your body, add 1 disc of that color to your population. Pause the video and record the number of each type of bacteria in your body in your data table.
So that was round 1. And if we go back to our data table here, under round 1, how many green, how many blue, how many orange after that round was completed. And so we see that there were 2, 4, 6, 8, 9 green, 7 blue, 2 orange. So you would do 9, 7, 2 for that. And then you would keep going and roll the die to simulate your 8 doses.
Round 2. It is time to take your antibiotic. Toss a number cube and follow the instructions in the number cube key. You forgot to take the antibiotic. Do nothing. The bacteria are reproducing all the time. If one or more bacteria of a particular type are still alive in your body, add 1 disc of that color to your population. Pause the video and record the number of each type of bacteria in your body in your data table.
So now our end of day 2, what do we have? You forgot your medicine. And when you forget your medicine, you can't kill any, but they're still reproducing. So I have 10, 8, 3.
Round 3. It is time to take your antibiotic. Toss a number cube and follow the instructions in the number cube key. The bacteria are reproducing all the time. If one or more bacteria of a particular type are still alive in your body, add 1 disc of that color to your population. Pause the video and record the number of each type of bacteria in your body in your data table. Round 4. It is time to take your antibiotic. Toss a number cube and follow the instructions in the number cube key. The bacteria are reproducing all the time. If one or more bacteria of a particular type are still alive in your body, add 1 disc of that color to your population. Pause the video and record the number of each type of bacteria in your body in your data table. Round 5. It is time to take your antibiotic. Toss a number cube and follow the instructions in the number cube key. The bacteria are reproducing all the time. If one or more bacteria of a particular type are still alive in your body, add one disc of that color to your population. Pause the video and record the number of each type of bacteria in your body in your data table. Round 6. It is time to take your antibiotic. Toss a number cube and follow the instructions in the number cube key. The bacteria are reproducing all the time. If one or more bacteria of a particular type are still alive in your body, add one disc of that color to your population. Pause the video and record the number of each type of bacteria in your body in your data table. Round 7. It is time to take your antibiotic. Toss a number cube and follow the instructions in the number cube key. The bacteria are reproducing all the time. If one or more bacteria of a particular type are still alive in your body, add one disc of that color to your population. Pause the video and record the number of each type of bacteria in your body in your data table. Round 8. It is time to take your antibiotic. Toss a number cube and follow the instructions in the number cube key. The bacteria are reproducing all the time. If one or more bacteria of a particular type are still alive in your body, add one disc of that color to your population. Pause the video and record the number of each type of bacteria in your body in your data table.
As you're recording your data, I want you to think about what just happened. I want you to think about that resistance of the bacteria. And now that you're done with your course of antibiotics, your 8 days of antibiotics, you're taking it, what do you notice and what is happening? And think about that as we move forward. We can graph our data. If you would like to make a bar graph of the data that you have, of the types of bacteria before and the types of bacteria after, that would be great. If not, don't worry about it. And now let us go to here.
What if I told you there were trillions of tiny bacteria all around you? It's true. Microorganisms called bacteria were some of the first life forms to appear on Earth. Though they consist of only a single cell, their total biomass is greater than that of all plants and animals combined. And they live virtually everywhere: on the ground, in the water, on your kitchen table, on your skin, even inside you. Don't reach for the panic button just yet. Although you have 10 times more bacterial cells inside you than your body has human cells, many of these bacteria are harmless or even beneficial, helping digestion and immunity.
10 times more bacteria than your own cells.
But there are a few bad apples that can cause harmful infections, from minor inconveniences to deadly epidemics. Fortunately, there are amazing medicines designed to fight bacterial infections. Synthesized from chemicals or occurring naturally in things like mold, these antibiotics kill or neutralize bacteria by interrupting cell wall synthesis or interfering with vital processes like protein synthesis, all while leaving human cells unharmed. The deployment of antibiotics over the course of the 20th century has rendered many previously dangerous diseases easily treatable. But today, more and more of our antibiotics are becoming less effective. Did something go wrong to make them stop working? The problem is not with the antibiotics, but the bacteria they were made to fight. And the reason lies in Darwin's theory of natural selection. Just like any other organisms, individual bacteria can undergo random mutations. Many of these mutations are harmful or useless, but every now and then, one comes along that gives its organism an edge in survival. And for a bacterium, a mutation making it resistant to a certain antibiotic gives quite the edge. As the non-resistant bacteria are killed off, which happens especially quickly in antibiotic-rich environments like hospitals, there is more room and resources for the resistant ones to thrive.
Remember what Darwin said, that it's evolution by natural selection. So in this case, natural is man-made. This selection of the resistant bacteria are going to change and evolve and survive. The bacteria that was not resistant get killed.
Passing along only the mutated genes that helped them do so. Reproduction isn't the only way to do this. Some can release their DNA upon death to be picked up by other bacteria, while others use a method called conjugation, connecting through pili to share their genes. Over time, the resistant genes proliferate, creating entire strains of resistant superbacteria. So how much time do we have before these superbugs take over? Well, in some bacteria, it's already happened. For instance, some strands of Staphylococcus aureus, which causes everything from skin infections to pneumonia and sepsis, have developed into MRSA, becoming resistant to beta-lactam antibiotics like penicillin, methicillin, and oxacillin. Thanks to a gene that replaces the protein beta-lactams normally target and bind to, MRSA can keep making its cell walls unimpeded. Other superbacteria, like Salmonella, even sometimes produce enzymes like beta-lactamase that break down antibiotic attackers before they can do any damage. And E. coli, a diverse group of bacteria that contains strains that cause diarrhea and kidney failure, can prevent the function of antibiotics like quinolones by actively booting any invaders that manage to enter the cell. But there is good news. Scientists are working to stay one step ahead of the bacteria. And although development of new antibiotics has slowed in recent years, the World Health Organization has made it a priority to develop novel treatments. Other scientists are investigating alternate solutions, such as phage therapy or using vaccines to prevent infections. Most importantly, curbing the excessive and unnecessary use of antibiotics, such as for minor infections that can resolve on their own, as well as changing medical practice to prevent hospital infections, can have a major impact by keeping more non-resistant bacteria alive as competition for resistant strains. In the war against superbacteria, de-escalation may sometimes work better than an evolutionary arms race.
Here's the question I would like you to respond to. Dr. Torres said the bacteria are evolving. What did the doctor mean by that? Go ahead and write your answer in, and we will continue evolution tomorrow.